Hi Bobcats. In this video we're going to look at lattice energy, which is the energy that's released when ions come together to build up a crystal structure. Our objectives are to define lattice energy and then to explore the effect of changing an ionic charge or an ionic size and how that affects the lattice energy. Lattice energy is defined as the enthalpy change, the delta H, for the process where a positive gas phase ion reacts with a negative gas phase ion to give us an ionic crystalline solid. Lattice energies are exothermic, so they will have negative values, and a bigger negative value means that it's a more stable crystal lattice. These graphs illustrate very clearly the effect of size on lattice energy. I want to draw your attention back here in the lower right-hand corner to Coulomb's law. That force of attraction gets to be bigger as the distance between particles gets smaller. So it's an inverse relationship here. Smaller particles, or a smaller separation between charged particles, results in a bigger force of attraction. It's going to give us a bigger lattice energy. So as we compare a similar series of compounds, so let's see over here on the left-hand side, the anion in all of these chemicals is chloride. So the thing that's changing from one to the next is the cation. We're going from lithium to sodium to potassium to rubidium to cesium. Now, as you move down the periodic table, these cations get bigger. In lithium, we're talking about having helium is that noble gas electron configuration for that Li plus ion, and helium is only occupying the 1s subshell, whereas by the time you get to cesium, the cesium ion's electron configuration is isoelectronic with the xenon configuration, and xenon uses the 5p subshell. So cesium is going to be bigger than lithium, and that trend will hold as you move from lithium to cesium. The cation is getting bigger, and so the separation between the cation and the anion gets bigger. And as that happens, the lattice energy gets smaller in magnitude. Now, these are all exothermic numbers, so this is showing us how much energy is released. And so less energy is released when cesium chloride gets formed than when lithium chloride gets formed. We see that exact same trend holding for changing the anion size. So as the anion gets bigger, going from fluorine to iodine, the ionization energy gets smaller. So a bigger space between charges means a smaller lattice energy, and a smaller separation between charges because you have a smaller cation or a smaller anion means a bigger lattice energy. If we look at the effect of charge on lattice energy, notice that charge is in the numerator of this equation, and so if the charges get bigger, then the lattice energy will get bigger as well. So if all other things are held pretty much constant, something that has a -2 charge will have a bigger lattice energy than something that has a -1 charge. Your textbook also goes through a couple examples of something called a Born-Haber cycle. This is kind of neat because it wraps the thermodynamics, thermochemistry back into this concept of bonding. In spring of 2020, I'm not going to hold you responsible for doing any calculations with the Born-Haber cycle because there are a lot of details in setting up these calculations correctly in order to get the right answer. And so this is something that I would need to spend a lot of time with you guys on in class, which we don't have the opportunity to do. So this is just simply taking advantage of the fact that enthalpies are a state function. So it doesn't matter how you get from one position to another position. And so if we look at the difference in energy between the top of this energy level diagram, the potassium ion in the gas phase plus chlorine atom in the gas phase, and down at the bottom, KCl solid. It doesn't matter if we take this pathway that's all in blue on the left, or if we take this pathway that's over on the right that's partly in blue and partly in green. Both pathways should have the same delta H. And so we can set that up knowing all of the numbers in these pathways except for the lattice energy so that we can solve for the lattice energy. And it's not hard, but it's tedious, and the devil is in the details on this calculation. So I wanted you to see the idea, but I'm not going to put this on a quiz or a test or a homework. So lattice energy is the energy that's released when an ionic substance gets formed. And if you're comparing the lattice energy of two different compounds, the one that has bigger charges, like if we were to compare, say, sodium chloride with magnesium sulfide. These are all elements that are very close to one another in the periodic table. Sodium is +1 and chlorine is -1, whereas magnesium is +2 and sulfur is -2. Since magnesium and sulfur have larger charges, magnesium sulfide would have a larger lattice energy than sodium chloride. And then if we're comparing lattice energy between an ionic compound where we have, say, a small positive and negative ion versus a large positive and a large negative ion, the one that has the smaller size will have a larger lattice energy. And then it was the opposite over here with charges. The one that has the bigger charges has a bigger lattice energy, and that's because of the form of Coulomb's law.